What time we get now?
12:50.
12:50. All right, trying to think of. All right, so let's talk about media pressure drop. That'll be a good thing to kind of wrap up everything on, and then we can have another session tomorrow. Okay, so we've got a bed of media, and we're trying to push air through it, okay? Now, pressure drop through anything, the force to push air through anything, any kind of solid like this, is basically an exponential function, okay? So if we chart velocity down here of the air going through the media bed, so the speed of the air going through the media bed, and we show that at like 20 feet per minute, 40, 50, 60, 70, 80, 90, 100, okay? You're gonna get a curve, and this is velocity, and this is what our pressure is gonna be, all right? So this is, I'm gonna just put PD, pressure drop, okay? And this is measured in inches of water column, okay? So let's explain what inches of water column mean, right? If you have a tube here, okay, and you fill it with, and you fill this tube, and this tube has an elbow in it, and you fill this tube with water right here, okay, and then you blow air into here, the pressure that it takes to make this water go up 1 inch is referred to as 1 inch of water column, okay? All right, so it's sitting at equilibrium here, and then you blow into the end of it, and you blow it, and it goes up three inches. That's 3 inches of pressure, okay? We call that 3 inches. So that's kind of similar to pounds per square inch, maybe like your car. You're putting air in your car, and it says it's got to be 32 psi. That's pounds per square inch. Well, that's a really high pressure compared to what we're dealing with. 1 inch of water column is like a tenth of a psi kind of type thing. So that's the scale. So that's why we work in this other scale rather than psi, because if we work in a psi, the numbers we'd be working with would be, you know, something like that, right? So you're working 1 inch of water column for it, okay? So if we're looking at what those values are for most of our media, and the pressure drop around most of our media is about the same. So let's call this 2, 1.5, 1.0, 0.5, something like that. We'll bring it down here. 0.5, 1. No, there you go. Okay, so I've mentioned to you kind of the maximum airflow that we push air through is about 100 feet per minute. The reason that we don't do more than 100 feet per minute is because the pressure drop gets kind of crazy after that. It gets super high because it's exponential. So the amount of pressure change from 60 to 70 is far less than the amount of pressure change from 90 to 100. Okay, all right. So it's going to be, so at 100 feet per minute, the number that we typically use is 1.8, okay? And that's for 12-inch deep bed, okay? So we have to, because you remember, you may have a 12-inch bed, you may have a 24-inch bed, you may have a 36-inch bed, okay? So that's the point for there. And then for 50 feet per minute, it's something like 0.6, I think, or so. We're not real good on having real good published numbers on that stuff, I tell you. So the curve is something like this, okay? So at 50 we're here, and at 100 we're all the way up here. And if you went to 120, it'd be something way up here with it, okay? So that's for every 12 inches. So if you are, let's say this is 0.6, okay, I'm going to call it 0.8 just for the sake of things. I don't want to throw it off. I'd rather overestimate it than underestimate it. So let's say it's 0.8. Okay, so if you had a 3-foot bed of adsorbent media, like our typical odor control systems do, and that was running through at 50 feet per minute, then the pressure drop of the adsorbent media would be 3 times 0.8, or 2.4. Okay, right? But if it was running through at 100 feet per minute, it'd be 3 times 1.8, which is 5.4. Okay, so there's a huge difference in pressure drop there. So when you're selecting your fans for your systems, part of selecting the fan, you have to two critical things that you have to know when you're selecting your fan. You have to know your airflow, which is just about always told to us, and then you have to know your pressure drop, okay, which is, this is the way that you calculate that pressure drop there, okay? It's usually a simple way to do it, and we need to come up with probably a better formula for you guys to have, because if you have a system that's at 75, we need to have a number to go with. But typically, most engineers don't understand this concept very well, and we just generally default to about 1.8 for everything, kind of type thing, because if you allowed for too much pressure drop, it just means they're going to have a little too much airflow.
Is the maximum efficiency of the of the media?
Yeah.
So maximum efficiency is at 50?
Not maximum efficiency, but an efficiency that we can live with, because your efficiency could actually even improve if you went below 50, right? If you wanted super efficient, then you could run it at 25. Okay, but we know that we can get, with a 3-foot deep bed of media, at 50 feet per minute, we can get 99.9% efficiency, removal efficiency. It's really good, 99.9. At 100 feet per minute, we'd probably do more like 99, maybe 99.5. But that's when the media is new, right? When the media gets used up a little bit, then that efficiency is going to drop off a lot quicker than that one will. Okay. So this makes a really efficient, really reliable system running at 50 feet per minute. Okay. What's the difference between a system that's 100 feet per minute and a system that's 50 feet per minute? What do you think the cost is between them? It's about twice. This system is about twice the cost of that system. It's twice as much media. The vessel has to have twice as much bed area. So, and the fan is, etc. So it's not quite, but it's significantly more. So making a really good system is a lot more expensive with it. Okay, so just have to keep that in mind. So that's enough for today. So tomorrow we're going to talk about side access units and cassettes. I'm talking about the pressure drop for those. There'll probably be a couple of other subjects that we'll throw into there as well too. All right?
We had an incident today as far as with Archie's going over, where an engineer had requested 12 inches of water column. And it's like, okay, what's up with this, so we can just say, yeah, you can get that, or we can say, well, here's what we're going to have in our system. You need all this extra 8 inches, on your end, or else,
Yeah.
So sometimes we need to clarify that. I've actually had them ask for 25 inches of water column before, which is crazy.
Yeah.
They're just thinking, oh, more must be better. So
Yeah. And so they say, well, we'll just allow for extra. But what does? So let's say the engineer tells us to design for 20 inches of water column, okay? And we know that our system is only going to take 6 inches of water column, all right? What is that? How does that affect us in the field when we get out there? What do you think happens when a system designed for 1,000 CFM, let's say that the engineer says, I want 1,000 CFM at 20 inches, okay? When We think it should be more like 6 inches. So when you install that system and you really only have 6 inches, what do you think happens to that system? Your airflow goes way, way up.
10,000, yeah.
Okay, because the same blower that gives you 1,000 CFM at 20 inches gives you like 3,000 CFM at 6 inches. Okay, all right. So then you're saying, well, yeah, what's wrong with too much airflow, right? No, but too much airflow is okay. Now that's all sorts of problems. Okay, remember your mist and grease filter. It's got to operate within that zone for 300 to 350 feet per minute kind of operation. So if you've tripled your flow and you size your airflow on 1,000, but you're actually getting 3,000, now your pressure drop going through your mist and grease filter is going to go through the roof. And you're not going to capture any of the water going into it because the water drops are going to race through there, right? So that becomes a problem. So
I mean, that would be a good way to something explain to the engineer right there, if it's in wastewater.
yeah,
So
that's right.
there would say,
Yeah.
he'd say, oh, okay, that makes sense.
So
Mr.
usually the way that
Basically.
usually the way we handle this, because we have limited ability to interact with some of the engineers, and most of these engineers think they know everything about odor control when they know nothing about odor control, okay? Keep in mind that a consulting engineer is an expert at nothing, okay? He runs around getting vendors to do all of his work for him, but he thinks he's an expert at everything, okay? And so this guy's like 20 inches, we're gonna design for 20 inches, oh, we've done all the calculations, we're going super conservative on this and we're gonna do it. So the way to reply to him is, yeah, Mr. Engineer, our system won't have anywhere near as much. We've gone back and we've redone this, and we think that this is the pressure drop, but we will design the system to use a blower which could do this if we get into the field and find out that it needs to, okay? So usually what happens is you've got a blower curve, and you know, we're the engineer, this is 1,000 CFM and 3,000 CFM, and here's 6 inches of water, and here's 20 inches, right? And the engineer wants to be here, 1,000, and so we'll select a blower that could do either of them at a different speed, and the worst thing you have to do is change the belt drive on the blower to to increase the speed of the blower to get him what he wants, right? Kind of type thing. So you're probably gonna have to put a big motor on there, because you've got to, that blower's got to have the capability to get to that level, but we're going to set it at this level, okay? And so we'll say, Mr. Engineer, we get out there, we know our stuff, and we're telling you it's going to be here. But if we get out into the field, I'm sorry, yeah, we're telling you it's going to be 1,000 CFM at 6 inches, okay? But if we get out there and we don't have enough airflow, then it'll be Pure Air's responsibility to change the belts and the pulleys on the blower. Or if you've got a variable frequency drive, we'll just speed the blower up in order to get the airflow, okay? And that's what the value of a variable frequency drive is on all of these systems, is that it gives you a tremendous amount of flexibility. It gives the engineer a lot of flexibility, because there's no way that 1,000 CFM is the optimal airflow, right? Maybe it's 900, maybe it's 1,100, who knows? And so if they will use a variable frequency drive in order to adjust the airflow in the field, then you can set that better. Okay? Not every fan can produce 6,000 CF or 3,000 CFM at 6 inches or 1,000 at 20. You have to do kind of a balancing act and work on it. So you'll need to be careful on your blower selection with that. Okay, we had a case up in North Carolina where the engineer literally wanted, I think it was 20 inches of water column. We repeatedly told him, no, you don't need this, you don't need this, you don't need this. We gave him exactly what he wanted. The airflow was super high, And it was super noisy as well, because this thing was taking off like a jet. And, you know, we documented, listen, we told you this was gonna be a problem. And then he was like, oh,
It's
well,
also extremely energy inefficient.
completely
I
energy.
mean, I work in, you know, I came from this industry.
Yeah.
And no engineer would want something at 20-inch
Right.
if they
That's
can
right.
do it at 6.
Yeah.
There isn't an engineer alive who would do it. It's, everything's about energy efficiency.
Yeah.
And that completely blows it out of the water.
Yeah, yeah. Unfortunately, most of the consultant engineers that we work with, have no concern for energy efficiency. They're only concerned about, is it gonna take out the odor, and is it gonna have enough air? So they're concerned, A, is it gonna have enough CFM? Okay, because if it doesn't have enough CFM, then you're gonna have ventilation problems, you're gonna have a buildup of toxic gases, those are their concerns, right? So they're gonna go really heavy on this and and overestimate it from there. So we just have to kind of protect ourselves on that to
And we're gonna
hopefully.
be out there at the end, regardless. If they're wrong, it doesn't matter, we're still gonna be, they're gonna suck us into it, to help us, do whatever. So,
Yeah, that's right,
yeah,
that's
We're
right.
still gonna be involved, we're not gonna get off.
Yeah, the best way to take care of it is try to get it done up front, because
Yeah.
if we go ahead and provide the system at 1,000 CFM at 20 inches, we're gonna get out there and we can say, hey, Mr. Engineer, we told you this was gonna happen. He's gonna be like, well, you guys need to fix this or we're never gonna use you in another project, right? And you're like, okay, great. I mean, here we are, we're gonna run around and go fix it for this guy, right? So just get it done up front. That's the best thing to do there, so. All right, so tomorrow is mainly SH and cassettes and things like that tomorrow.
Thank you.
Yep.
Thank you.